Okay, ladies and gentlemen, welcome. This is Eddie's class, and I'm going to take you through exponential distribution. You are welcome for this lecture. When we speak of exponential distribution, we can refer back to the concepts of Poisson distribution. It's like a slight extension or modification of the Poisson process. While the Poisson process models the number of events within a given period of time, exponential distribution, on the other hand, it is basically concerned with modeling time between events, the time interval required for an event to occur. So as you can read from the slide, it says exponential distribution is basically a distribution that is concerned with time between events in a Poisson process. So we basically think of how much time do we need maybe to wait until a specific event of interest has occurred. So, for instance, this says there is a strong relationship between Poisson and exponential. Here is just an example to illustrate what the linkage between Poisson and exponential. Now, while Poisson, for instance, if you think of birthdays to be your outcome of interest, maybe you are in the hospital, you're in the hospital. Okay, in our case here, let's say you are working in a labor at Mumbai National Hospital, where we observe mothers giving births. Now, you may be interested to find out the number of births given in a unit period of time, for example, within an hour or within half an hour, 3 minutes. It depends on the duration of our interest. So when you speak of number of birthdays given in an hour, for instance, that's the Poisson process. Okay, it models number of events between a given period of time occurrence. How many events are there? So Poisson answered the question of how many events per time. Okay, but when you come the other way around, you think of the interval between each birth. Okay, so you have the question of how many. That, for example, I have 10 birthdays, I have 5 birthdays, or I have 6 birthdays. That's Poisson distribution. So when you speak it in the other way around, you try to find out the interval between the birthdays. Okay, from one birth to another. Now that one refers to exponential distribution. So if a mother, let's say mother X, has just given birth, okay, of his baby, a boy or a girl. Now when you think of after how long should you wait for the other one to give birth, that's the Poisson process. Sorry, it's an exponential process, exponential distribution. But when you think of number of births, the total number of children born, okay, in an hour, for instance, that's a Poisson. But when you think of the time interval between births, one birth and the other one, that is a Poisson, an exponential distribution. So that's the difference between the two. Poisson is most concerned with numbers in a given period of time, but with the exponential, we are most interested on the time period until an event of interest occurs. Okay, if you are traveling, for instance, you are waiting for the bus, then you can think of after how long should you wait for a bus to come and pick you. if you're letting it train, then after how long will the train pass by and just pick you. So that's the most important thing you have to note regarding Poisson and exponential distribution. Now here are just some few additional remarks that with the exponential distribution becomes more appropriate when events are independent and random with a constant rate over time. That you expect the rate of an event to occur will be nearly constant or for the given period of time. Okay, so that is Poisson distribution. Now here are just some of the questions that Poisson can try, sorry, exponential can try to answer. For instance, if you think that how much time will elapse before an earthquake occurs in a given region. Okay, let's say you are living in region A and the earthquake has just occurred, let's say today. So if you think in your mind that after how long will an earthquake occur, okay, it means you are interested in the time period for which you have to wait for the earthquake to come. Now that's a Poisson process. Such kind of a question can be answered by exponential. Sorry, not Poisson, exponential. I'm used to Poisson, so that's exponential process. Okay, the other question that can be answered by exponential distribution is how long do we need to wait until a customer enters in our shop. Okay, that you have a shop somewhere you are selling. Okay, then you need to think out that after how long, for instance, after saving a customer, okay, then how long should you wait for the next one to come in? Okay, such kind of questions can be answered or can be followed by exponential distribution. Here are just some two additional questions that you can think of to be or to follow under exponential distribution. Now, this is the most important thing, perhaps the most important side, okay, that if you assume that the answer to this question is unknown, that's number one, and you think of the elapsed time as a random variable, that you think that the time which has passed is a random variable, is first is unknown, then is a random variable with an exponential distribution as long as the events occurs continuously and independently at a constant rate. What does it mean? It means if you think that this question, the answers to these questions, yes, they're just here, answers to these questions, okay, all these are unknown. Okay, you don't know after how long a customer may enter your shop. You don't know after how long an earthquake can occur. You don't know after how long it can take before a call receives a next phone call. You don't know after how long a piece of machinery works without breakdown. Then if you don't know all these and you think it to be random variables, then you can think of the elapsed time for you to wait maybe for an earthquake, for a phone call, for a customer, to be a random variable with an exponential distribution. That's the point. Okay, so simply exponential refers to time period you are waiting for an event of interest to occur. We make that simple. Okay, fine. Now here just for some example, just to clarify more, but the most important thing you can take from this slide is that with Poisson we are interested with a number, okay, occurring in a given period of time, but with the exponential we are interested on the time period between events. This speaks about student registration. That, for instance, think of that you register 50 students in a given hour. Okay, so with that number, 50 in an hour, 50 per hour, that's the Poisson process. But when you think of how many students registered, so the time interval between registration, that after a student has been registered, one student, then how long should we wait for another student to register? That's an exponential thing. Okay, so if you have 50 per hour, then you find that the average time it takes for the 50 to register, then it makes like 1.2 minutes. So 1.2 is an exponential process, and 50 falls under Poisson. So the last two lines clarifies more, or just means on what I've been speaking, that Poisson process are people, while units for exponential are minutes. That is the difference. Poisson, you refer the numbers. Exponential, you refer the time. Okay, to make it clear. Now, after having some brief introduction on what Poisson or exponential and the difference between the two, we can now define a random variable that follows exponential distribution, and this is the probability density function for that particular variable that follows an exponential distribution. It's f of x equal to 1 over theta e to the minus theta x for all x is greater than 0 and 0 elsewhere. Now, with this one, I have a single parameter which is theta, and remember, theta is the average, okay, the rate at which events occur. The average, it's the average expectation, you can say in the other words, okay, of the events which they occur. Okay, how many events maybe per time period. That is our theta. On average, you have this number of events at this one. Okay, so that's our parameter of interest. But we can present the same equation in the other way around by trying to find out the number of items or the number of events in a given hour. Those number of events. Remember, theta is an average number or expectation, in other words, we can call it. Okay, but you can write under the same equation the probability function in another form, and here it is. Okay, we have the cumulative density function and we have the probability density function in this slide. The first one is the cumulative density function, the second is the probability density function. Now remember, a Poisson, sorry, not Poisson, an exponential distribution, we have the cumulative density function, which is given by 1 minus e to the lambda y. Now, for y greater than 0 and 0 for y less or equal to 0. I will clarify this. Now, if you differentiate the cumulative density function, then you end up having the probability density function. Now, if you differentiate this one, f of y equal to 1 minus e to the y, lambda y. If you differentiate 1 becomes 0, and e to the y, lambda y becomes lambda e to the lambda y, which is negative. Now, in this example here, I used x, but here there is y. No matter what the annotations, they are all random numbers. So whichever letter you use is fine for you. You can use x, y, z, but to maintain, to be consistent is also fine. So I could have been used x instead of y, no problem. But this is the probability density function, the one which is below, and the one above is the cumulative density function. Why minus this much? Because with exponential distribution, it always gives an area to the left of the distribution of the graph. Okay, this way I have 1 minus e to the lambda x, meaning that is the area to the left. The total area in the graph is always equal to 1. So if you need something, the area from time 0, let's say, to time 1, you think of the area to the left, let's say from 0 to 1. From time 0 to time 4, it will give you the area to the left of 4. Time 0 to time 6, it will give you the area to the left of 6. That's why we always take 1 minus that one, because we are referring to the area to the left from the cumulative density function gives the area to the left. Now with this one, you can see in the previous slide we had 1 over theta, but here we have lambda. So simply you can say theta equal to 1 over lambda, or lambda equal to 1 over theta. Now lambda now is the number of events occurring in the given period, while theta in this case is the average, okay, average number of events, but theta is the total number of events occurring per given number of time. In other words, theta refers to the Poisson process, while lambda refers a Poisson process, and theta, as you can see from here, refers an exponential distribution, while theta refers an exponential lambda refers an exponential, a Poisson process. So if you have lambda, you can come back to find theta by using that kind of expression, or you can simply use the same equation, provided that all the parameters are well addressed. So these are the two equations that are mostly used. Okay, in some text they use this one, but some literature they use this one. It depends on the situation or the nature of the problem at hand. So whichever one you use, you always end up having the right thing. So that is a brief introduction for exponential distribution. We have seen the density function, we have seen the meaning and how it's different from Poisson. Now here are some questions. We have question 1, we have question 2, question 3, and question 4. So I'll go back and try to give you some solutions to this question, especially when we do 2 questions, 1 question 2, to see how we can apply these formulas in coming up with the probabilities depending on the given conditions. So let me go back and find my examples right here. Yes, here are my examples. I have the example 5 right here, and I'll just show you the solution for the first 2 examples so that you can go on with the next 2 examples. So the first question says, let x be the amount of time in minutes that a postal clerk spends with his or her customer. The time is known to have exponential distribution with average amount of time. You can see from here, with average amount of time. Let me find here a pen. Okay, this is the keyword somewhere here. The one that will guide you either to use the first equation or the second one. That either to use this equation right here or to use this one. Okay, so this is what will be guiding us. Now from here we have been given the average amount of time. Now this will be equal to theta. Okay, average amount of time equal to 4 minutes. You can see 4 minutes. These are the important information. Average amount of time equal to 4 minutes. In other words, it says theta equal to 4 minutes. Now number one says state the probability density function. That's number 1. Question 2, find the probability that a clerk spends 4 to 5 minutes with an randomly selected customer. That on average the clerk spends 4 minutes. That's the average. So we are required to find the probability that once a customer goes for being saved, then he can spend up to 4 to 5 minutes. That's the question. Now We'll go step by step to see on how we can solve that one. First, we shall use these two formulas. We shall start with the first formula and the second one, and then I'll show the alternative for solving the same question by using the cumulative density function. So just follow me, and it's my anticipation that you'll understand. So from this question, it says average amount of time in minutes per customer is 4 minutes. Now that is theta, the mean. So mean equal to 4 minutes, and that's from our equation of the decay parameter, which is 1 over theta, will be equal to 1 over 4, which is 0.25. So you can use 1 over 4 in the equation, or you can use 0.25, no problem. Whichever one you find that it is easier for you to write. Now we call our PDF probability density function is this one. Okay. Should I change the color? Let me change the color for my this one. Even should I change the color? Let me find where can I change the color. Oh, just here. I don't find where to change the color. Okay, we can proceed. Okay. Now, this is the PDF, the probability density function. Okay. Now, question 1 says state the probability density function. So to state the probability density function, means we have to substitute the given information in our PDF. So theta equals 1 over 4. In other words, you have to substitute our parameter. Now, upon substitution, we have this question, which is 1 over 4 times e to the 1 over 4x. So in other words, instead of using 1 over 4, you can use you can use this one, 0.25. Now this is the PDF. Okay, we are done. Example 2 says, sorry, not example 2, question 2. Find the probability that a clerk spends 4 to 5 minutes with a random selected customer. Now what I've said is the exponential distribution, it models or it gives area to the left. That thing, this is an exponential distribution. Let me try to write right here. It's like this. Now we are required to find the probability that x equals between 5 and 4. So if this equal to 4 right here, that this is times 4. Okay, so if you substitute this 4 in a cumulative, if you consider about the cumulative function, it means it will give you area to the left, to this area, to this side here. It will give you area to the left. Again, for x equal to 5, think if 5 is somewhere here, this is 5. Again, it will give you the area to the left. I need to change the color for you, for me to that is clear, but I can't see where. Just forgot. I think it is no. Where can I change this? View, from view, protect, not share, no, connect, no, extra. Oh, where now? Comment, import, summarize. It's unfortunate I can't see. Where can I change the font color? I just want to change this one to be okay. No problem, you can proceed, but I will try to find out. I will try to find out. Let us proceed. Okay. Now the issue is, the question is, we have 4, we have 5. Let me take back my pen. Okay. We have 4 right here, and you have 5. This is equal to 5. So if you consider equal 5, again it will give you the area to the left. Area to the left, like this. This is area to the left for t equal to 5. Now, when you are asked to find out the probability between 4, that the probability that a clerk spends 4 to 5 minutes, it means, in other words, if I sketch here my Poisson, and let's say this is 4 somewhere here, okay, and we have 5 somewhere here, then what we are required is to find this area in between. That's what we are required to find. Okay. So from mathematics point of view, and if you consider back, remember this formula here, that if we have the PDF, the probability of a given an event will be equal to integral from a to b f of x dx, from the lower limit to the upper limit f of x dx. Now our concern is to find the probability between 4 to 5. So it's simply that we integrate from 4 up to 5 f of x dx. Now what's the f of x? Here it is. This is f of x. So we simply integrate this one from a will be equal to 4, the lower limit, and b will be equal to 5, which is the upper limit. Now let's see. So it will be integral from 4, the lower limit, to 5 f of x dx. Now what's the f of x? It is this one. That's our function, the x. So if we integrate this and you substitute the values, okay, we'll have this expression here and this. Then upon simplification, we have the final output, and this is our required probability. Okay, I think with integration, no problem with you. You have done integration, and you integrate these, then you substitute the values 4 and 5. Then you have this expression. If you simplify the first one, you have this. If you simplify this, you take e to the -1, you have this. And subtraction, we have negative outside here, it gives 0.8. So in other words, the probability that a clerk will spend 4 to 5 minutes in serving a customer is 0.08, very small, okay, 0.08. That is the probability. Now I have used the PDF, the probability density function, in computing the probability. Alternatively, what I told you earlier while discussing some concept, that you can also use the cumulative density function. That we can use this, the function, instead of using this formula right here, you can use the cumulative density function to find the probability for the given event. Now how to go about, let's see. That alternatively, we can use the cumulative density function to compute the required probability. It should be noted that the cumulative density function gives the area to the left, as I have the demonstration here, that the CDF gives the area to the left. So if it gives the area to the left, what next then? This is the CDF, 1 minus e to the lambda power x. Okay. What I told you is these x's they're just variables, so they can be changed depending on what your variable of interest or how. Okay, so this is the PDF, which is this one. Now when we think of the probability that a customer maybe can be served for 4 minutes, it means this x becomes equal to 4, and if you think of 5 minutes, this one becomes equal to how much? 5. So in other words, the probability that a customer will be served between 4 to 5 minutes will be the same as taking f of 5, okay, minus f of 4. How? Remember, we had this kind of a drawing, that this is our exponential distribution. It goes on decreasing. Now this is t equal to 4, and here is t equal to how much? To 5. we have said exponential gives areas to the left of this. Now if we need the interval between 4 to 5, then we have to consider this area. Okay, so this will be equal to f of 4, and here we have f of 5, so it will be the opposite, and this minus this is f of 5. So you take this minus that one. So if we substitute f of 5, means it's a big thing here. F of 4 is this one. So here is f of 5, and here is f of 4. So simply take 1 minus e power 1 over 4 times 5 minus 1 minus e to the 1 over 4 times 4. Upon simplification, this one goes with this. We have e to the a quarter times 5, it is this. Okay, and this expression here, it is this one. Oh, so this should be 4. This should be 4. That should be okay, fine. So it's fine. This one, the first expression, it is this, and this one, the last one, is this one. Okay, now if you substitute, sorry, if you subtract, you have e or 1 over 4 times 4, it is this one. 1 over 4 times 5, it is this. Then upon simplification, you have this, which is the same as this one. So what does it mean? It means you can use the cumulative density function in computing the probabilities, or you can use the probability density function. With the probability density function, you must integrate, but with the cumulative function, you must substitute the values for which you have been given. Now that's example 1, and I think it is over. Let's mark the end of example 1. We can move on to example 2. We can move on to example 2. Now what is it saying? It says at a certain location on highway 110, the number of cars exceeding speed limit by more than 10 miles per hour in half an hour. You can see in half an hour, that's the time period, that's between 0 minutes to 30 seconds, sorry, 30 minutes, is a random variable having a Poisson distribution with the lambda equal to 8.4. So it means the number of cars exceeding a speed limit of this much in half an hour is approximately equal to this much. What if the probability that waiting time of less than 5 minutes between the cars exceeding speed limit for that particular time interval? So this is the one from which this formula can be applicable. This one, you can see the difference. In the first one, we were given the average time, okay, but here I've been given the number of cars in half an hour. But this, let me go back to the question and see the difference. Here we add the average amount of time required. You can see average amount of time equal to 4 minutes, on average of 4 minutes. But with this one, what is it saying? We have the number of cars exceeding speed limit in half an hour. Okay, in half an hour. Now let's go on. So the number exceeding speed limit of that much in half an hour is this one, meaning lambda equal to 8.4. So if we let y to be our random variable, then this will be the probability density function, and this will be the, yes, upon substituting our variable of interest, which is lambda, we have 8.4, okay, to the that much for y greater than 0, y less or equal to 0. But I think this should be otherwise, not greater than 0. This should be otherwise. I'm sorry. So if we integrate, remember we have to find that the probability of less than 5 minutes. So see, at the same as the previous one, it is integral from a to b, f of y dy. So we move on. Now the question says find the probability that what is the probability of waiting time less than 5? Less than 5 means it is from 0 minute to 5 minutes. So this is 0 minute, y, which is a variable of interest. Now this is 1 over 6. Why 1 over 6 not 5? Because this 8 given subtending to this time period, which is, where is it? Here it is, half an hour, and this is the Poisson process, which is a lambda equal to 8.4. Now with these 5 minutes, we have to convert this into half an hour. Like how many minutes if we convert into hours, and our time for comparison, it is half an hour. So we simply take 5 divided by 30, okay, which makes 1 over 6. So that's why this one comes in. Simply 5 divided by 30. So this is 5. Okay, so it is 0 up to 1 over 6 f of y dy. We integrate this from 0 to 8. Now upon integration, we have this expression right here, okay, and we have this for 0. Now when you simplify this, you have this one, which is the probability. Now the most important thing to note is when to use this formula and when to use the previous one. Okay, so it depends on if you are given the average time, okay, between events, then you simply use the first one. But if you are given the number of objects, number of whatever number you are given, depending on the question, then this one becomes much applicable. And as you have seen from the previous question, that we can also use the cumulative density function. So even for this question, then we can use also the cumulative density function, and here it is, okay, this is the cumulative density function, that is f of y equal to 1 minus e to the y. Now remember, we are trying to find out the time, so the probability that the time is between 0 to 5, less than 5. So in other words, we have to find this probability. It is from 0, let's equal to y, let's equal to how much? To x. So it is simply f of how much? F of 1 over 6. Okay? F of 1 over 6, or f of 5 minutes. That is the meaning. That if I draw this, it's like this, and here is our Poisson. It goes that way. This is 0, where it starts, and this is 5 minutes. Now we have to find the probability that waiting time is less than, what's it saying? Probability that waiting time less than 5 minutes between cars of exceeding the speed limit. So we have to find the area to the left. That is from 0 up to how much? Up to 5. So it's simply, you take f over, you simply take f of 5. Okay, if you take f of 5, will give you the area from 5 all the way up to 0. From 5 all the way up to 0. So f of 5 equals 1 over 6. So it equal to 1 minus e to the lambda times 1 over 6. And here it is. And if you simplify this one, you have the last equation. Now, these are the two examples, and I've shown you how to use the probability density functions and how to use the cumulative density function. All the two methods or procedure can be used. You can use either the cumulative density function or probability mass function depending on your preference or which one finds better for you. Thank you for listening. here are the examples for you to make some practice. Okay, now is there a practice you will have to go through? We have done this number 1, we have done number 2, we have left with number 3 and example 4. These are for you to practice. Here's example 3. You can make some practice right here, and this example 4 you can also have some practice. Next year we'll be speaking on the mean and variance for Poisson distribution, but also I take you through the momentous property of a exponential distribution. Thank you for listening. Be with me next time.